So welcome to the second keynote speech of Oriental COCOSDA 2021. This is Haizhou Li from the National University of Singapore. Today, I'm very glad to chair this session. The second keynote speech is delivered by Professor Jun Du from University of Science and Technology of China. I have known Professor Du for a long time. He's in the field of speech processing, and I think also see him in recent years working on computer vision and other multimedia topics as well. I also remember that when I was the editor-in-chief of IEEE Transaction, he was in my editorial board as an associate editor of the journal. Professor Du is also a distinguished lecturer under OPSIPA Distinguished Lectures series of this year. So we are very glad to have him to deliver a speech here. It is also considered as a OPSIPA Distinguished Lecture. So without further ado, I would like to pass the time to Professor Du. Please.
Okay. Yeah. Thanks, Professor Lee, for your detailed introduction. Yeah. Okay. So good afternoon, everyone. Yeah, I'm very glad to see you all virtually. Yeah, and has this opportunity to make an online presentation. My today's topic is environmentally robust speech recognition from a perspective from a corpus-based perspective. Okay. So before my talk, first let me introduce my research background. Currently, my team is mainly working on multimodal text recognition, which aims to make machines convert different model signals to text structure, semantics information, just like the human beings. For example, the automatic speech recognition using speech signals, handwriting recognition using trajectory input signals, and optical character recognition using image signals, and lip reading using video signals. Yeah, actually, these research topics are the key components of artificial intelligence. Today, I will focus on talking about the speech recognition part. Prior to joining USTC, I also worked for iFlyTech Research and Microsoft Research Asia. So I have some both academic and industry backgrounds. This makes me have many collaborations with universities and other research institutes. So thanks very much to all my students and collaborators in academia and industry. Yeah, I cannot make today's presentation with their great efforts. Okay, so this is agenda today. First, I will give an overall introduction. Then I will divide the development of the environmental robust ASR into two stages, namely before the deep learning era and in the deep learning era. The detailed analysis of both corpus and technical development will be given. Finally, the summary and the future research trend will be discussed. Okay, let's start with the formulation of automatic speech recognition. Actually, ASR is a special pattern recognition problem. From the viewpoint of information theory, the generation of input speech signal X is actually a noisy channel encoding problem. So recovering the underlying word sequence W from X, namely the ASR process, is a channel decoding problem. Yeah, so in information theory, the channel decoding is formulated by the posterior probability of W given X. Then, based on the plug-in map decision rule, the solution to ASR is to maximize this posterior probability to search the optimal word sequence W hat. which is equivalent to maximizing the product of two items, PW and PX given W. Yeah, PW is a language model, while PX given W is a acoustic model. So in this talk, we will focus on the acoustic model, which is related with environmental robustness. Okay. So what is environmental robustness? It is well known that one ultimate goal of environmentally robust ASR is to solve the cocktail party problem, namely achieving the human level auditory perception. So the concept of cocktail party effect was raised by the cognitive scientist Colin Cherry in 1953. It refers to the ability to focus one's attention on a particular stimulus while filtering out a range of other stimuli. So this is an extremely challenging mission for the machine to finish, as the machine needs to simultaneously filter the environmental distortions, for example, the background noise, room reverberations, and the multiple speaker interferences. Okay, so from the perspective of pattern recognition, the environmental robustness issue is arised due to the environmental mismatch between training and testing. To improve the robustness, we have two ways. The first way is to design of robust signal capturing, design of feature extraction and the model architecture itself. The second way is to transform the signal or the model parameters in corresponding signal feature or model space to reduce the mismatch. For example, we can transform the input speech signal SY in the testing environments back to the training environments using a transformation TS. You can also transform the model parameters MX from the training environment to the testing environments. Okay. So accordingly, we can divide all the existing environment robust techniques into two broad categories. In the first category, for example, we can capture the noise robust signals using a bone throat microphone or a laser Doppler vibrometer sensor. We can also extract noise robust PNCC features besides the MLCC and the PLP acoustic features. For model design, the noise robustness of conventional GMM, HMM can be improved by deep learning, for example, using the DN-HMM model or CTC or the very recent, very popular encoder and decoder models. Actually, in this talk, we will pay more attention to the techniques in the second category, namely using transformations. So in signal domain, the transformation will be specifically defined as speech enhancement, speech de-reverberation, and speech separation, which correspond to three environment factors, that is background noise, room reverberation, and the speaker interference. In feature domain, we can conduct feature enhancement, feature normalization, and feature compensation. In model domain, we can perform model compensation and model adaptation. So here, please note that I listed the multi-style training method. Actually, this method is a very simple and effective way by collecting or synthesizing multi-style training data with different environmental distortions, which is widely used as a product solution to increase robustnesses of ASR systems. Finally, for the hybrid feature and model space transformation, the joint uncertainty decoding method can be explored. For more details of all these methods, you can refer to this overview paper. I highly recommend this paper if you want to have a deep understanding of the earlier stage development of environment robust techniques before deep learning. Okay, from another perspective, we can also divide all the techniques into two broad class. One is based on the explicit distortion model, and another one is based on implicit distortion model. In explicit modeling, the environment distortion model is given as a mathematical fundamental. For example, the additive signal model is assumed for the background noise and the multi-speaker scenario. The convolutional signal model is to describe the distorted signals with room reverberations. But in realistic adverse environments, the distortion model might be much more complicated by nesting multiple types of signal models. Yeah, so another type is based on the implicit model. Yeah, here in implicit modeling, we often refer to the case that the stereo data set is provided. Yeah, namely, the relationship between clean speech signals and distorted signal can be implicitly modeled based on the stereo data. In real applications, the collection of diversified stereo data is quite time-consuming and expensive. So we will focus on the discussion based on the explicit model later. Okay. In these slides, I show, yeah, okay. So previously, we talked about simply discussed the environmentally robust speech recognition in a more technical way. So actually, I worked in this area for about 18 years. So in these slides, I would like to explore its development in the past 2 decades from a corpus perspective. Yeah, the speech corpus is quite important as it provides a benchmark for verifying different techniques. So the corpus and technical developments are highly blended. Overall, we can see that in the first decade, as the standard databases for the research of environment robust speech recognition was preliminarily released, most corpora aim at simple ASR tasks with small vocabulary and simulated small scale training data with a single environment factor. Also in this period, the GMM HMM was still employed as a conventional acoustic model. So most environmental robust techniques were based on statistical models. And most of them are far more from being effective for realistic applications. And you can see in the second decade, due to the faster development of computing, storage, and deep learning techniques, the application demand for environmental robust techniques is quite urgent. More and more challenging corpora were released, which led to the fast technical development in recent years. Now I will give a detailed analysis on the corpus and technical development in these 2 stages. Okay, first let's talk about the development in the first stage before the emergence of deep learning. In these slides, I show a timeline for corpus and technical development. A series of Aurora databases are very representative, as many environment robust techniques were verified on them. Although there are other databases such as speech separation, challenge corpus, and AMI meeting corpus. The research on them is relatively limited. As for the technical development in this period, in each year, I select one representative method and give the links to the verified corpuses and the method type it belongs to. For example, Splice proposed in 2000 is a feature compensation approach based on the stereo data mapping using Gaussian mixture models. ETSI-FE is an advanced front end proposed by ETSI using two-stage winner filtering method. HEQ stands for the histogram equalization, which is a feature normalization method, and VTS representing the vector Taylor series, which is adopted for approximating the nonlinear distortion model, can be used for both feature compensation and model compensation. CMMSE is a feature compensation approach using the capture domain MMC criteria. NAT refers to noise adaptive training, while NMF is a speech separation method using non-negative matrix factorization. So for more details of this method, you can refer to this overview paper. Now, the analysis will be conducted on the representative Aurora databases. Yeah, Aurora is the name of ETSI STQ DSR working group. This working group released 4 standard databases from Aurora 2 to Aurora 5 between 2000 and 2007. This corpora was designed for performance evaluation of distributed speech recognition and noisy environments. Aurora 2, Aurora 3, and Aurora 5 are tasks for digital string recognition, which adopts a very small vocabulary of 11 digits. Both Aurora 2 and Aurora 5 were tasks for digital string recognition. Both Aurora 2 and Aurora 5 are simulated data by adding noise signals to the TI digits clean speech data. The difference of Aurora 5 from Aurora 2 is the usage of hands-free microphone in combination with further speech transformation over GSM cellular network to a remote recognition system. The Aurora 3 data is recorded in realistic car environments. Only Aurora 4 corpus aims at LVSSR task with the simulated noisy data from a Wall Street Journal 0 speech database. In the final column of this table, the current Google Scholar citation number of each database introduction paper is given. From this number, it's easy to observe that Aurora 2 and Aurora 3 are 2 most popular corpus for the researchers to verify their ideas. Okay. As the most popular corpus in early stage, Aurora 2 simulates the noisy speech data by adding 8 types of noise signals from the real world to the English speech of digital string from TI digits with 7 different SNR levels. 2 systems are designed, namely the clean condition training and multi-condition training. The difference between them is whether the noise signals are added to the speech data in the training set. So clean condition training is a highly mismatched setting between training and testing, while multi-condition training is a matched setting. In this table, we compare the word error rates of different competitive feature space and model space approaches and the 2 training sets. Generally, the model space approach performs much better than feature space approach, but it's commonly very time consuming and cannot be applied in realistic applications. Yeah. For the Aurora 3 database, it consists of speech data from 4 languages, namely Finnish, Spanish, German, and Danish. Aura 3 is a subset of speech data car corpus, which are recorded by both close talking and hands-free microphones in realistic car environments for 10 Western languages. 3 settings between training and testing are designed, including well-matched condition, media mismatch condition, and the high mismatch condition. Similarly, we list the performance comparison in this table. We can observe that the performance gap between model space and the feature space approaches is relatively small comparing to the Aura 2 database. Yeah, so the Aura 3 task is generally more challenging than Aura 2 task due to the realistic recording setting. Okay, here we can make some interesting observations from earlier stage development. First, most standard data sets are simply designed. Second, most techniques are verified on simulated digital string corpus due to the limitations of techniques, computing storage resources, and application demand. Thirdly, although the methods are diverse, most of them are based on statistical models, such as Gaussian model, Gaussian mixture model, and GMM HMM model. Finally, we can see that even for the easiest Aura 2 task, it still lacks of practical solution because many model assumptions are made for both explicit and implicit modeling. Okay, now let's talk about the development in the deep learning area. If we consider the earlier stage development is relatively slow without producing too much practical values, then in deep learning area, the development is accelerated. With the big data and the high performance computing cluster, deep learning technologies with domain knowledge are applied everywhere, namely for both front end and back end of ASR systems. This makes the ASR techniques cross the practical threshold in more and more applications. So the remaining challenging scenarios, for example, the far field and the multi-speaker interaction in home and meeting, led to the emergence of more and more challenging corpora. From the timeline of corpus development, we can observe that in most recent years, since 2018, the speech corpora along this direction are intensively released, such as Cham 5.6 challenge data, DieHard 123 challenge data, Library CSS, and the Airshell 4 database. So how is the performance of existing techniques on this data set? I will discuss it later by taking the Cham challenge as an example. Before that, I will first talk about how deep learning plays an important role in front end and back end of ASR systems. Okay, so let's revisit the explicit distortion model here. As I mentioned before, the explicit model is a mathematical fundamental for all existing environment robust techniques. And each explicit distortion model corresponds to one research topic in terms of recovering the underlying clean speech signals S from the distorted noisy speech signal X. For example, the additive noise model is related to the speech enhancement problem, while the convolutional reverberation model is related to the speech dereverberation problems. So in realistic adverse environment, the explicit model could be very complicated. Then the speech preprocessing to recover the clean speech of each speaker from the existence of background noises, reverberations, and interfering speakers is extremely challenging. So before deep learning, all these three research topics, namely speech enhancement, dereverberation, and separation, often use probabilistic models to model the speech signals, noise signals, and the room impulse response. Due to the complicated relationship among these different signals, many model assumptions should be made, and this determine the problems are quite difficult to solve, leading to the unsatisfactory ASR performance. Moreover, the methodologies for these three problems are also quite different. But after the emergence of deep learning, a natural idea is whether we can provide a unified framework for all these regression problems, namely the front end of the ASR system. Okay, so the answer is yes. Yeah, as you all know, the first successful demonstration of deep learning techniques is its application to acoustic modeling or backend of ASR. We called it a deep classification model, where the output is a class posterior probability of acoustic unit or hidden states bounded between 1 and 0. So inspired by this, in 2014, our team proposed the deep regression model to solve the speech enhancement problem as a high-dimensional vector-to-vector mapping problem. Here, the model input is a noisy speech feature vector, while the model output is a clean speech feature vectors. Comparing to the deep classification model, deep regression model is more difficult to train because the output features are unbounded. In our implementation, we do the feature normalization to both input and output feature vectors to guarantee a stable learning curve. To train this regression model, we need to prepare the input and output data pairs. Here we employed the explicit distortion model. Actually, in these slides, yeah, we use the explicit distortion model to artificially generate the noisy speech data based on a clean speech dataset and a noise signal dataset. Yeah. Later, we found that this deep regression model can solve not only the speech enhancement problems, but also the speech dereverberation and the separation problems. The only difference is that the explicit distortion model could be changed to generate the corresponding training data pairs. So at that time, although our proposed approach significantly outperformed the conventional speech enhancement approach in an experimental study, we still lack of the theoretical justification of deep regression model. So 5 years later, the theoretical justification parts are supplemented in our 2 journal papers. The first paper is about the discussion of the representation power of deep regression model. We extended several famous theorems on universal approximation in 1980s and 1990s to the DN-based vector-to-vector regression. The related bounds are proved and linked with speech enhancement experiments. In the second paper, we discussed the generalization power of the deep regression model. We analyzed the upbound of the mean absolute error by the error decomposition. 3 error items, namely the approximation error, estimation error, and the optimization error, are comprehensively investigated. Okay, so after we proposed the deep regression model, we found that its generalization capability to realistic mismatched environments is not good. So accordingly, our subsequent research mainly focused on how to fully utilize the domain knowledge of speech signal processing in the architecture design and the parameter learning of deep regression models. our goal is to achieve explainable, compact, and high-performance deep architectures. As for the domain knowledge, we studied the auditory features and the masking-based features, different measures such as noise signal, signal-noise ratios, and the T60. Also, the gender speaker information. We also tried to integrate the probabilistic modeling in conventional approaches with deep learning and perform the joint modeling of front end and back end. Finally, the spatial information in microphone array techniques could also be utilized. Later, I will show some examples in the discussion of challenge. Okay, from now on, I will make detailed analysis to corpus and corpus development in deep learning area. Here, I take the CHAM challenge as an example. A CHAM challenge is a successor of speech separation challenge. It focused on speech separation and recognition in daily listening conditions. From CHAM 1 in 2011 to the latest CHAM 6 in 2020, tasks are become more and more challenging. In CHAM 1 challenge, the task is to recognize simple command words, just like SSC, and the noisy data is collected by binaural mannequin in family home environments. On top of CHAM 1, CHAM 2 challenge increase the difficulty by adding an LVCSR task based on Wall Street Journal corpus and allowing small speaker movements when recording the noisy data. CHAM 3 and CHAM 4 share the same LVCSR task based on Wall Street Journal corpus, and the noisy data is recorded in realistic public spaces. CHAM 5 and CHAM 6 also share the same LVCSR task. And the noisy data is collected in a more challenging dinner party scenario. The last column of this table showed the best word error rate of the champion system for each challenge. Our USTC team won the first place of CHAM 4, CHAM 5, and CHAM 6 tasks. In the following slides, I will make a deep dive into these recent 3 challenges. For the okay, so first for the CHAM 4 challenge, for the data collection, the speakers are holding a pad with 6 microphones in different positions. They are reading the text from Wall Street Journal corpus in 4 public spaces, namely sitting in a cafe, standing at a street junction, traveling on a bus, and walking in a pedestrian area. Our champion system reduced the word error rate to 2.2%, reaching the practical threshold for this task. And the key innovation of our systems is the so-called iterative mask estimation. Actually, our solution is built on top of the CHAM 3 champion solution, namely the complex Gaussian mixture model based masking estimation for beamforming. A CGMM-based masking estimation is a statistical modeling-based approach, which can be further improved by deep learning-based masking estimation as post-processing. It can also be refined by the VAT information as a frame-level mask from the recognition results of ASR systems. So we designed this iterative procedure to improve masking-based beamforming by deep learning and ASR system feedbacks. Okay, and for CHAM 5 challenge, for the data collection, a set of 6 Microsoft Kinect devices are placed in 3 different locations, namely kitchen, dining area, and living room. Each Kinect has a linear array of 4 microphones. In each dinner party, 4 participants are allowed to freely chat. So the collected data is far-field and in conversational style, and with a large portion of speech overlaps. Yeah, here is an example. Yeah. Okay. From this example, we can see that recognizing such recording is even challenging for human listening. So the official baseline ASR system yielded a word error rate of more than 80%. 80%. Yeah, given the Oracle speaker derivation. Although our final solution reduced the word error rate to less than 50%, seeking for this solution is not smooth. Yeah. So during the period of CHAM5 challenge, in the first 2 months, our team investigated on the CHAM4 challenge solution and many other techniques. But as shown in these slides, which is a summary from the team won the first place. Only the simple WPE method for speech dereverberation can get a marginal improvement. So what is the main reason for this observation? Yeah, this is because all previous methods did not work on CHAM5 corpus, adopted a simple explicit model, only focusing on one environmental factor, such as background noise or reverberation or speaker interference. However, the recording of CHAM5 corpus simultaneously includes all these distortions. Yeah, and we need to consider the joint modeling of multiple environment factors. Okay, so with this idea, we finally proposed a knowledge-rich front end by jointly speech denoising, dereverberation, and separation. And this is a key technology why our system can yield significant word error rate reduction over the baseline system. We can see that this solution needs a quite complicated procedure. Yeah, for the details, you can refer to our paper. Another interesting observation from CHAM5 challenge is that advanced acoustic language models using powerful deep architectures did not work without a well-designed front end. This demonstrated that the front end design is extremely important for ASR systems in adverse environments, similar to the cocktail party problem. Okay, for CHAM6 challenge, one more challenging track, namely derivation and recognition, is added. Our team won the first place of track 1 for recognition with Oracle speaker derivation. And our new solution reduced the word error rate from 46 to 30. And our front-end solution for CHAM6 is that we propose a novel space and speaker-aware iterative mask estimation for CGMM-based beamforming. This approach can deeply incorporate spatial and speaker information into the input and output design of neural network-based mask estimation. Okay, so that's all for the second stage development. Finally, I will give a summary and a prospect of environmental robust speech recognition development. First, the current techniques can solve the problem for relatively easy tasks, namely the scenario with single speaker near field with background noises and the reading style speech. Second, for the most challenging corpus designed for LVSSR tasks with multiple speaker interaction, multiple environment factors, and multiple microphone arrays, and the conversational style speech, the performances are still far more from being used in realistic applications. The third observation is that the techniques are rapidly advanced in an application-driven way. The deep learning centered method, by fully utilizing the domain knowledge, has been proved to be quite effective in many realistic corpora. However, the problem is the solutions seem to become more and more complicated in an iterative manner. Okay. Okay. Finally, I will talk about the future research trend. So my personal viewpoint about the future research trend of environmental robust speech recognition is listed in this slide. In recent years, we can see that many speech corpora are jointly released by the academia and the companies with both data and technology background. In technical part, taking the recent GSOT 2020 workshop as an example, more and more researchers from industry, such as Microsoft, Google, NTT, are eager to participate and even take the lead for the research of environment robust speech recognition. So I think in the future, stronger collaborations between academia and the industry will be built to promote both corpus and technique development for realistic problems. For the technical development part, the joint modeling of multiple environment factors should be further investigated in a more mathematical way. Also, the joint modeling of front-end and back-end is important, which can make the front-end better serve for ASR metrics. Finally, to alleviate the technical difficulty, we can consider to provide more specific information, such as the target speaker information, target environment information, and the multimodality information, such as video and semantics information. In this way, we might accelerate the application of existing techniques. Accordingly, I think in the future, more corpora along this research direction will be released. For example, the target scenario corpus, target speaker corpus, and the multi-modality corpus. Okay. Finally, I would like to make an advertisement of our recent MISP challenge this year. MISP aims at solving the speech processing problems in adverse environments by providing auxiliary multimodal information, such as video and text information. MISP 2021 is accepted as a signal processing grand challenge of ICASP 2022, which targets the home TV scenario with a multi-speaker chatting in Chinese while watching TV. We designed two audiovisual tasks, namely audiovisual wake word spotting and audiovisual speech recognition with Oracle speaker diarization. The deadline of challenge is February the 1st next year. For more details, you can refer to our challenge website. After this challenge, we also have a plan to release all the data set publicly. Researchers are warmly welcome to work on this corpus. Sorry. Okay, that's all for my talk. Thanks.
Thank you. Thank Professor Du for the wonderful talk. It is very informative. Give us a corpus perspective and a historical perspective of the challenge. I would like to invite some questions from the audience. We have 15 minutes for discussion.
Okay. I have a question.
Yeah, Satoshi, please.
Hello, Fred. It's a great talk. Thank you very much. So I'm interested in deep regression.
Mm-hmm.
So So there are many factors: noise, speaker, and contents of the speech, and noise contents, and SNR. So how much this deep regression model works? For example, if you use this noise regression model for chime evaluation, how much does this work?
If we let's back to this slide. Yeah, actually, in this slide we can see there are several modules. For example, here the SE model here, speech enhanced model, and here some speech separation model. All this model is based on the deep regression model. Yeah, so I think the here is the key of this model can be successfully applied in the challenging is that we need to jointly considering all these environmental factors. Because if we only consider the additive noise, you cannot get a better result. You need to jointly considering all these environmental factors, and I think this is the key. And for the deep regression model, I think it's just a tool for you to get a better mapping, between the different signals. Yes. For example, I think for example here you can see that for the Cham4 challenge, here is the key idea is iterative. Iterative is the key idea. I think it's not the specific architecture of the deep learning architecture. Iteratively, you can how to say you can fully utilizing the complementarity between the statistical models and the deep learning models.
Okay, so this is okay. Deep regression model is only a tool, and then you use the regression model for various factors in this final model. Okay, thank you very much.
Thank you.
Some more questions? Let me ask a question. So just now the slides that you mentioned about a regression model, but it seems that your diagram used a regression model to predict a mask. So I thought that mask is a counterpart of regression model. Some people do regression, some people estimate mask.
Yes. I can give an explanation. Yes, because before our method, the Professor Liang Wang from OSU, they proposed a mask-based method. He published the paper in 2013. So because here I also mentioned in this slide, we can change our output here. I mentioned that we can use the masking-based features rather than the direct the spectral feature mapping here. We can do some multitask learning in the output. In one way, we're predicting the clean speech features. In other, we can predicting the masking-based features. For example, the ideal binary mask or the ideal racial mask. But from the concept of regression, even you predicting the mask-based features, it still belongs to the deep regression model. Because here the mask, the difference is just that the masking-based features is they are bounded. They are bounded by between 1 and 0. But I think this is still belongs to the deep regression model.
Some questions from the audience. Okay, I have some more questions. So I understand that the new task, the recent task, we also have speaker diarization, and this is this is an old task. And in today's, I mean, as the research progresses, we now have a better way to kind of eliminate the speech by speakers. So, for example, in the past, if two persons talking at the same time, then diarization usually is not very. If you only try to mark the beginning and the end, it's very difficult. So in the new task, what you are doing, how do you deal with overlapping speech when you evaluate diarization?
Okay.
Overlapping. Yeah.
Okay. Very good question. Yeah, very good question. Yes. Actually, we are now currently working on this. Yeah, this is a very good question. Because in the traditional speaker diarization, they just give the label, of each frame. How many people are on that frame? Yes, talking within that frame, but they do not separating the speech. Yeah, so for the overlapping segments, they just give more than 2 different speaker labels. Yeah, but they do not separate them. So in our, you can see that because for example, in the track 1, here in the track 1, you can see that the speaker diarization, Oracle speaker diarization is given. So for the non-overlapping segments, we did not how to say, we need not to do anything. Yeah, just for the overlapping segments, we can use the speech separation. Yeah, speech separation to separate, and then with separate 2 stream speech signals, we use the ASR system to recognize them. Yeah, and finally we can get a word rate for each streams. Yeah, this is a way we do that. So in our for example, in our this diagram, we use a speech separation model here. Yeah, SS model is to do the speech separation on the overlapping segments. Yeah. Hopefully I answer your question.
Good, thank you. Yeah, other questions? Please. We have 5 more minutes. So Charm 6 has ended, and do we have a new plan for future? Charm 7.
I talked with Shinji, which is one organizer of Charm 6 challenge. Previously, he told me that they have some plans to do the audio visual. Yeah, because they record the data using the Microsoft Keynote. Yeah, there is a video cameras. They should have the data, but I'm not sure. Yeah, they will release such task in the future. Yeah. I just asked him maybe 1 year ago. Yeah, 1 year ago. But for now, I have no news from this, because
your MISP has audio visual speech recognition task. Am I right?
Oh, okay. Yeah.
Yeah, the challenge, the ICASP challenge.
Oh, okay. Here. Yes. So this is the reason why we designed a Chinese version. Yes. So Chinese. Chinese version similar to the Chime challenge. Yeah.
Okay.
We hopefully Chime will also release the audio video data. Yeah. Previously, the organizer told me that maybe there's some licensing problem. Yeah. So you know that the video information is very sensitive. Yeah, for the for the users. Yeah, recording the data. Yeah. So for our challenge, we also ask our data collection users to sign a contract. Yeah, they will allow us to do the research, but do not use it in the business part. Yeah, so
That's very good.
yeah.
Can you take one more questions?
Okay, may I have a question?
Yeah, good. Hi.
Yeah. We are working on the single microphone. So should we work on front end or back end to get the better improvement in noisy environment? Because currently we just use multi-style training that work, I think good enough. How do you think?
Yes, I know your question. Yes, because in the multi-style training conditions, the baseline is still the water aperture is still very low. So if you want to do the noisy reduction to achieve a better water aperture, yeah, it's very challenging. So here I list one way. Here I mentioned as joint modeling. Yeah, you can. I do not list here. In last year, we have 2 papers. Yes, 2 transaction papers. One is to combine the traditional deep regression model based method with conventional method called based on the statistic models. Yeah, using the teacher-student learning. And we found that if you combine the conventional statistic models and deep learning, you have the chance to improve the recognition accuracy over the multi-condition training setting. Yeah, this is one way. Another way is you can jointly optimizing the backend and front end. Yeah, and for the industry, yes, they often do not want to modify the backend, right? So last year we had one paper. We fixed the backend and we optimizing the front end, and the guidance of the backend metrics, and we get some improvement on the CHAM4 challenges. Also, we received some emails from other institutes that they think our these 2 methods indeed can improve the performance in realistic problems. Yeah, hopefully my answer your questions. Yeah.
Okay, thank you.
Okay, I think it's time. It's already it's 2 minutes. I would like to end the session. I would thank Professor Du for the wonderful talk, and the conference will send you a token of appreciation will post to you. So we will need to get your Professor Du's postal address. We will arrange separately. So thank you very much.
Okay, thank you, Professor Lee.